Yes, hi Asmita. Alright, so I've ticked the energy symbols box. We have an energy source, and in this case it's the falling water. We have the energy converter somewhere in the middle. It converts one form of energy to the other. And finally there's the energy destination, which is where the energy lands up. Alright? This set of four at the bottom are four different energy sources. You can see there's falling water, which is what we have here. That's the first one. But you could also have sunlight, you could also have a kettle, yeah, which is another form of heat, or a person paddling a bicycle, and that's joined to the converter. Okay, and we'll see that in a couple of ways. You could have a couple of converters, a solar converter and a mechanical energy converter, mechanical energy to heat converter, which is what we're using here. And then final destinations could be many. One is from water that's heated, or a bulb that's lit, yeah, or a fluorescent lamp that's lit. Many different energy sources, yeah. These are all that's shown here. Now the point, here's the reset all switch. That's the play pause switch that you need. Each of the energy sources has a rate control. You can see the one here that controls at what rate water falls. These are the different forms of energy, okay, and they are color coded. Gray is mechanical, blue is electrical, red is thermal, and so on and so forth. All right. Now, as I said, the ones we are going to use for this experiment, our energy source is falling water. We have a mechanical energy converter, and this is pretty similar to a hydroelectric dam, really, yeah, or a hydroelectric power plant. Okay. It converts this falling water into electricity, which then, this is a heater, and that heats up the water in here. That is our setup. Okay. Now let me just start very briefly just to see what's happening here very quickly. Can you see the water falling and the paddle wheels start to move? Okay, very good. Can you see that some of this mechanical energy is getting converted to blue electrical energy? Yes? No? And can you see that in the heater, this blue electrical energy is becoming red thermal energy? Yes? Now we can also see a couple more things. One is some of the water is getting wasted, which means the energy is not being captured by the converter. And if we wait for some time, we'll see some energy. You can see the steam evaporating. After some time, you'll see energy, thermal energy go away in that fashion. Let's just wait for that and see what happens. Okay, it's taking a while. Observe on where the steam is coming out from, and there it goes. Yeah, so energy goes away, thermal energy goes away as the water evaporates or the steam takes away some of the heat energy. Is this clear what's happening? What are the various energy movements that are occurring? And all logical. We see all this happening around us. So there's nothing here that is something which is magical or something you don't understand. Okay? Alright, so there's one point here that I would like to talk about before. So I'm going to hit reset all. And I'm going to talk about one point here. You can see that energy is represented by, each unit is represented by a block. Can you see this? In the water, for example, there's a whole lot of energy in the water. Yes? Rather than as a flowing thing, it's represented as a bunch of discrete block-sized things. Alright? Now, this may seem a little bit weird at this stage, but this is an important property of energy itself. Okay, energy is quantized, which means, and this is something that you will learn more when you get to the 11th standard, what that means is that energy flows in discrete quantities. Now what those quantities exactly are depends. It's not the same every time. But energy can only flow in chunks. You cannot have a continuous flow of energy, even though it may seem like that. So for example, as an example, maybe, so if you're sitting in your car, yeah, and you can look at the speedometer while you're driving, you can see that it's possible for all speeds to occur, right? From say 0 to 60. It might be 60, it might be 60 an hour, it might be 59 and a half, it might be 30, it might be 30.75. Yeah, it could be any arbitrary value, correct? And you know that kinetic energy is 1 by 2 mv squared, which means that for any given value of v, you have a specific value of kinetic energy. What I'm actually telling you by saying that, look, these blocks exist means literally that you can have either 101 joules of energy or 102 joules of energy, but not 100.5. What that means is that and I've not done an exact numerical calculation. What that means is that the car can either go at 50 or 55, not at 53. That sounds a little weird, doesn't it? And it does. It is a difficult idea to digest, which is why I'm not going to dwell on it too much at this stage. You'll understand it much better when you get to the 11th standard. All I want to explain is, many students tell me, but sir, this representation of energy is not correct. You can keep breaking it up. Point is, look, yes, you can break it up, but there arrives a time when you cannot break up those blocks anymore. Okay? It's only to dispel that this experiment is not right. Some students actually come up with that, which is why I make this point. Okay, so now we're going to start off this experiment. What I'm going to do is I'm going to release this tap, okay, very slowly, and I'm going to count 15 energy units from the falling water, okay. I'm going to count how many of them do not get captured by the paddle wheel, and I'm going to count how many escape from the steam over here. Okay, here we go. Start it very slowly. That's one. That's two, and one didn't get captured. That's the third, which got captured. And that's one that's lost, you can see, the evaporation. That's one that didn't get captured. One more that did get captured. That's a total of 5 done. One lost through evaporation. That's another one lost. As in didn't get captured. So that's a total of 7 so far. That's 2 that we lost to evaporation. Eight, it's 9. That's 10. That's 11. One more lost to evaporation. 12. 13. One more lost. That's 14. 15. Okay, I'm just going to wait till this is done, till it finds its way. We lose one more to evaporation. There. Okay, so what exactly happened? All right, here are my numbers that I observed. Okay, I had counted the number of energy units in the water to begin with, and that was 14. Okay, let me just reset all and we'll count. Let's count the number left now first. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, I make 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 16. Okay, there are 16 in energy units in the water. Can you see that? Yes? Alright, so let's now do some calculations. Okay? The number of packets of energy that got released here, right, by this were a total of 16, right, by the falling water. That was our starting number of packets. The number of packets not captured was 8. Alright, 8 went into the converter, 8 were not captured by the converter. Okay? We lost 5 through evaporation. Right? 5 of them through evaporation. We counted those. And the number of energy blocks in the water now left with us are, what did we say, 16, right? Was that correct? Is that what you counted, 16? Okay, so now let's see how this translates into application of the first law. What we're going to do is we are going to, let's look at, we'll define the system as the converter plus this water, okay, in this beaker, whatever it is. The converter plus the water in the beaker, that's our definition of the system now. Let's see what's the energy input here. There were 16 that came in and 8 were lost. So that was a total net energy input of 8. Do we agree with that? Eight of them just went through this way, yeah? They didn't enter the converter. So we put in 16, we lost 8. So we put in a total of 8 units of energy into the converter, into our system. Alright? How much was lost in evaporation? We counted 5 lost in evaporation. Alright? So the total number that, the total amount units of energy that got converted to heat, okay, were the 8 we put in minus the 5 that we lost. Okay, 8 minus 5. Do we lose 5? Do we lose 6? I'm sorry, I need your help to calculate figure out how many we're losing. Let me just restart this. I apologize. Okay, let's start again. I have messed up somewhere in keeping track. This is one of the issues called experimental error. Okay, let's start again. Let's count the number of energy blocks in here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Agree with this? There are 14 energy blocks in the water to start with. Alright, so I'm going to start again very slowly. Can somebody say, Kirti, can you keep track of how many escape, yeah, from the water? And Mayank, maybe you can keep track of how many are lost, yeah, they don't get captured by the converter. Alright? Okay? Kirti, ready? Here we go. 1, 2, 3. I increase the speed. That's 1. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, I need wait for the 16th one as well. 16. Okay, we won't count this guy. Okay, didn't hit the converter. Okay, let's just figure out. Mayank, how many were not captured by the converter out of the 16? 8. Kirti, how many did we lose in evaporation? 4. Alright, so now again we define this as our setup, the converter plus the water. Our energy input was what? 16 came in, 16 minus 8 that were not captured. That's 8 units we added to the system. Do we agree with that? How many did we lose? Of those, we lost 4 units through evaporation, correct? So the net number of units that we added was 4, correct? That was 4. Now can we calculate how many are left here in this water? How many energy units are left? Can somebody calculate and tell me? 18. Okay, does that make sense? We started with 4, we added 8, lost 4, so we should have 18 left. Does that make sense? Yes, rest of you, does it make sense? It may seem extremely simple here, but that is what is the important point to keep in mind here, is that you have to consider all forms of energy. When the energy started coming in, you see it was gray. When it was being converted into electricity, it was blue. Then it's being converted into red, which is also being lost as red thermal energy. So if you account for all forms of energy, total energy is conserved. Do we agree with this? Does this not make sense? And that is what the first law of thermodynamics says. What does it say? What is the delta? What is our delta E? All right, let's define this as the system. What is the work done on the system? The work done on the system is the total number of packets captured by the converter. Yes, do we agree with that? Yes, no? What was that number? So what was small w? Work done on the system was 8 units. Yes? Exactly. How much heat did we add to the system? Remember, our system is the converter and this beaker of water. We didn't add any heat. In fact, we lost some heat. No, Mayank, 8 was the work done on the system, right? What was the heat? Or maybe you're answering the previous question. I'm sorry. We lost some heat, right, through evaporation. And we lost 4 units, correct? Didn't we lose 4 units? So which means the delta is, so Q in this case equals -4. Do we agree with this? Q is -4, W is 8 for the system that we have defined. Yeah? So what should delta E be? Remember, first law of thermodynamics says delta E equals Q, which is heat added to the system, plus W, which is work done on the system, which in our case is 8 plus -4, which equals 4. What is delta E? We started with 14 units of energy in this water. We ended up with 18 units. That change is delta E. Alright? Is it clear how the first law applies to this choice of system? Rest of you, clear or not clear? Okay, very good. Now, let's do a little bit of a change. Let us now define our system as this water alone. Okay, only this water. Alright? If we take this water, what is the work done on the water? Are we doing anything with the water? Are we stirring it or anything of the sort? What is the work done on the system? Are we stirring the system? No, we are not, right? Because we're not considering the converter. It's only this, that's our system. Which means that Q is 0. I'm sorry, W is 0. Do we agree with this? That there's no work being done on the water. Yeah? How much heat did we add to the system? So from the bottom, how many blocks of energy came in through this heater? Everything captured by the converter came in here, right, through the heater. That was 8 exactly. So Q in this situation is 8. Okay. However, we have to adjust for the Q lost to evaporation, which was 4. Yeah. So the net Q is 8 minus 4. That's 4 units. Is this clear how Q is 4 units for this system? 8 units of heat added through the heater at the bottom, 4 units lost through evaporation leads to a Q value of 4. Now apply the first law. Delta E equals Q plus W. For this choice of system, Q is 4, W is 0, and that gives you delta E equals Q plus W equal to 4. Again, the first law appears to hold. Right or no? So the point is this, regardless of what system you choose, the first law must hold because it is a fundamental law of nature. What are you doing really? You're just accounting for all possible forms of energy. That's all you're doing. And if that is conserved, then what you're saying is that energy cannot be created but can merely change form. And if you account for all those forms, the total amount of energy in any given system must, or the total amount of energy is constant if you consider all energy changes. That's really what the first law says. What I want you to appreciate is that this equation, first equation of thermodynamics that you learned, delta E equals Q plus W, is really stating that total energy is conserved. Yeah? Do you appreciate that point? That's what it means. That's what the first law of thermodynamics means. It means, look very, it sounds very, I don't know, awe-inspiring, first law of thermodynamics, but that's all it's saying. All it's saying is that total energy is conserved. Nothing more, nothing less. Is this clear? Okay, very good. Now we can replace, let me just hit reset all. Now here, so I can replace this falling water with a kettle. Okay, and there's a little nozzle here, and this nozzle now drives this energy converter. This is in fact exactly the same principle as a gas turbine. This is how a gas turbine works. This is how your thermal power plants work. Okay, there's heat, it converts in a boiler, it converts water into steam. You leave the steam onto the blades of a turbine. That turbine produces electrical energy. That's generally how electricity comes to your house from a thermal power plant. Okay, so now I'm not going to do this calculation business again, which you can do for yourself, but I just want you to see the energy changes that are occurring, all the energy points that you have to consider to get the first law right. So I'm again going to click the energy symbols, going to add some heat. Now watch what's happening. So some thermal energy is going in to the kettle. It comes out of the nozzle with some speed. So now it's mechanical energy. The red energy has become gray. Yeah? Note that red is thermal, gray is mechanical. Some of that is caught by the turbine, some is not, and that you can see is escaping. The turbine is converting each energy packet that it gets into blue, that's electrical energy, and this heater then converts it back into thermal energy. Okay, so essentially what you're saying is everything, that's all the heat that is produced here. Okay, and we assume that this is the only place where heat can get stored. It's not getting stored anywhere else. What does that mean? That means the temperature of everything else remains the same, right? Because if something stores heat, then its temperature generally rises. Yes? So when you say that nothing is storing heat, you're basically saying, look, everything's at the same temperature. Its temperature doesn't change. That's what you're saying. But if you look at what's happening, this thermal energy, if you account for the input as this, what's coming in from here, the output is what stays here, and minus what is lost, which is some of this and some from evaporation. If you take all these sources and destinations, you'll find that the total source must be equal to the total going into these three destinations. That is the first law. Is this clear? It's the same as the last experiment. I've just replaced the energy source with a different one. Instead of using mechanical energy or purely mechanical energy, I'm taking thermal energy, converting it first to mechanical energy and using that in this case. But the same numbers will hold. You can do the same set of calculations, and that's exactly what you need to do in the lab. Alright, so I'm not going, let me just replace things again just to show you something else. Let's use solar power. Now if you use solar power, will a mechanical converter do? Can you see the converter moving? It doesn't, right? Because this is thermal power, and this converter can only convert mechanical power to electrical power. Or I'm sorry, mechanical energy to electrical energy. Are you getting mechanical energy from the sun? You need matter moving at some speed to get mechanical energy. Are you getting that from the sun? No, you're not. So this converter is useless for us. Yeah, it's not going to work. What we need is a solar converter. Now let's see what happens. Can you see that now some of the solar energy or the light energy is getting converted into electrical energy because we're using the right converter? Yes? No? And then the same stuff is happening. The electrical energy is going into this heater. This heater, water is getting heated, and you can see that some of this is escaping. Yes, Sanjana, you will get a slight lag. That's the nature of how online classes work. Alright, so that's really all there is. It's just, again, different sources of energy, perhaps different uses of energy, but everything must add up according to the first law. Is this all clear or not clear? This basic idea that that energy must add up. Okay, very good. Now here's what we're going to do. Now let's just go back to the class window. Now pause this. Let's go back to the class window and see how does this apply to chemical systems. Okay, at the end of the day, we are studying chemistry after all, right? So how does this apply to chemical systems? Let's try and just understand that. No, don't close it yet, because I'm going to be doing another experiment. So don't close it yet, please. Okay, so let's talk about purely chemical systems. We talked about mechanical, thermal, electrical systems in the lab. Let's talk about a purely chemical system. Okay, let's consider these two chemical reactions. Right? The first one, zinc plus HCl gives you zinc chloride plus hydrogen. This reaction occurs, okay, in nature. But if you take gold and drop it into HCl, this does not occur. It's the same thing, it's the same reaction in principle, but this doesn't occur, whereas this one does. Okay? So what can we say? Now let's first try and look at what's happening. What are the energy changes that are occurring? First, can you see that in both cases hydrogen is being produced? Yes? Hydrogen gas is being produced. So there's gases on the right hand side, but there's no gases on the left hand side. Okay? So do we agree that the volume of the system or volume of the products is much more than the volume of the reactants in both cases? There's a gas on the right hand side which has a lot more volume, right, than a liquid or a solid under normal lab conditions. Now clearly this hydrogen existed somewhere in the chemicals in the reactants, but now it exists by itself on the right hand side. So clearly, to exist and have some volume, it must have pushed the atmosphere back, right, to make space for itself. Do you agree with that? It should have pushed the atmosphere out. Yeah? Okay, so what is that? Therefore, it must have done some mechanical work. Do we agree with this? The hydrogen gas has pushed other gas molecules out and therefore must have done some work. Agreed? I mean, very simply, if I had just put in, for instance, if I had just taken the reaction, okay, I had taken a piston like this, put some weights on top, yeah, this is the piston, here's where the reaction took place. This expanding hydrogen gas would have pushed this piston up and moved these weights up by some distance, yes? Do you agree? And so this chemical system would have done some mechanical work, which means that small w, the work done on the system, must be negative, because work done by the system is positive. So work done on the system must be negative. So this is a negative number. Okay? Now, there is no heat being added to the system. We're not adding any heat to the system. Yeah, look at the system. There's no heat being added. There's no burners anywhere. So Q is 0. Okay? Q is 0. Now, therefore delta E, if you apply the first law to this both these chemical systems, then delta E has to be negative. Do we agree with that? There is no other way for if we apply the first law and we say that conservation of energy must take place, then it's clear that delta E must be a negative number. Okay? Now it turns out that in this reaction, the delta E change is enough for the system to do this work of pushing the atmosphere out, but in case 2, the delta E is, or the lowering of delta E, the delta E value is not enough to do this work of pushing the atmosphere out to create hydrogen, space for hydrogen. Therefore, the first reaction occurs, the second reaction doesn't. Is this clear or not clear? Okay, very good. Then you'll ask the question, the natural question that comes up. Okay, sir, if this reaction doesn't occur, then how does the first law hold? Okay, let's see that. If the system does not push this hydrogen out and make room for itself, then the work done is 0. Agreed? And work done on the system is 0. It's not a negative number. We already said Q is 0, so W is 0, Q is 0, delta E is 0, which means the reaction just does not occur. Isn't that consistent also with the first law? All right, very good. So I hope you understand how we are taking this idea of thermodynamics and conservation of energy and how it actually applies to chemical systems. Yeah, obviously this is a very simple appreciation. There, if you get into details, it's obviously a little more complex than this. But really, I've brought it down to a very simple way of understanding why some reactions can take place, some reactions cannot take place. Okay, and as we saw in this case, the lowering of energy here is enough for this mechanical work to take place, to push the atmosphere out to make room for hydrogen. In the second reaction, delta E is not enough, therefore it doesn't occur at all. Okay, I hope that point is quite clear. All right. Okay, so we are going to now do a second lab. Yeah, second lab. And I'm going to talk about entropies here. Give me a few minutes to set it up. Okay, this lab is on Join Me. Could you please go? Yes, Kirti, we did this lab last year, but we did it for another reason. Every experiment can explain several scientific laws. All right. Can everybody please confirm to me that you can see the experiment on the Join Me screen? Does anybody need the link again? It's there on the top of the chat. Scroll back in the chat, you should be able to see it. Rest of you, can you see it? Rohan, can you see? Please answer using the chat in the WizIQ classroom. Okay, very good. Everybody, it appears, can see this. All right. So now we are going to initially set this control to neon. Okay, it's neon atoms in here, the blue ones. You can see that. All right. We'll also set the control to solid, all right? So which means we're talking about the solid state. That's what we're talking about, all right? Okay, what is entropy? If you remember from your class, entropy is the extent of distribution of energy. Do you remember this idea from class? Yes? No? So there are two terms in there that are important. The first is there has to be energy, okay, and second, it has to be distributed. You need to account for both those ideas. Let's look at this solid here. All right, clearly, can you see that, you know, there are a lot of particles, so there is a lot of motion. As we saw, more the particles, the greater the amount of motion. That should be fairly obvious, right? Now, the more vigorous the motion of the particles, okay, what does that mean? That means each particle has a lot more kinetic energy, correct? Isn't that what it means if the particle motion is vigorous? And therefore there is greater energy that is distributed, and that means that there is more entropy of the system. Do we agree with this? If the motion, vigorousness of motion increases. Okay? Alright. Now you can see here that the particles are only vibrating, which means they have only motion along a straight line. They aren't really rotating and things like that, right? Can you see that? There's no real rotation, at least you can't figure it out. And there is none, yeah, because it's just one atom. So what is it? It can hardly rotate. Okay, so there's no rotation. But as we'll see for other substances, if there is, do we agree that if there is translational kinetic energy, which means they are vibrating, and rotational kinetic energy, which means they're also rotating, that means that the total energy that is being distributed is much greater? Do you agree with that? Or we can say that the energy has been distributed in many ways, partly rotational, partly translational, correct? We can say that, that's also a fair statement. And therefore that would mean that the entropy of the system is greater, okay? Because the distribution of that energy is much more. The energy may be greater, and the distribution, the ways in which it is distributed, is much greater. That together brings about this idea of entropy. Remember, again, I repeat, it's the total amount of energy and how much it is distributed. What are the ways in which it is distributed? How many particles is it distributed over? These are the considerations that go into judging entropy. It's when I say judging, we don't have an entropy number. We are not able to kind of put in a measurement stick or like a thermometer which gives us the entropy. So we have to make a judgment call. Okay, so I'm just trying to give you the parameters that will help us make a judgment call on what has more entropy. Does it have a unit? Absolutely, Kirti. If it has, its units are joules per Kelvin. Okay, joules per Kelvin. All right. Here we go. So what I'm going to do now, well, here let's look at this. Let's now focus on what we see in front of us. There is some motion, but it's very moderate, right, for every particle. Yes, do you agree with that? And so we can make a judgment that this is a low entropy condition. Solids by themselves have or are in a low entropy situation. The overall entropy of pure solids is low. We can make that judgment call. Is that fair to say based on what we see? It'll hopefully become a little more clearer, but this is a first level judgment that we can perhaps make at this stage. All right? Okay, so now what I'm going to do is I'm going to use this state control, change it to a liquid. Now it's still neon gas, but can you see that the motion is much more vigorous? Much more vigorous motion. And so would it now be fair for me to say that because the motion is more vigorous, it appears that the total amount of energy that has been distributed is more, okay? And therefore, this is now a higher entropy situation. Okay, we'll wait for you, Kirti. Rest of you, can you see this? What's happened when it's become a liquid? Oh, you too, Sanjana, all right? So we'll wait a few seconds. Let's go try and work around the lag. Okay, so can you see that the motion is much more vigorous now? And would you agree with me when I said that, okay, it's much more vigorous, each particle has a lot more kinetic energy, which means that a lot more energy has been distributed in this case as compared to the previous solid case, which means that the entropy must be higher. Yes? Is that a reasonable statement to make? Okay, now I'm going to make it a gas. And I'll give it some time. Let me know when all of you can see very vigorous motion all over the place. It should be obvious that it's become a gas. So I'll wait till all of you confirm to me that you can see this. Okay. Most of you, some of you can. Waiting for the rest of you. Asmita, yeah, you said yeah. Okay, Sanjana. Okay, everyone can see it. Do we agree that the particles have a lot more, they're moving much faster, there is a lot more kinetic energy on average that each particle has? Do you agree with this? And therefore, can I now state that in a gaseous form, there is a lot more energy that has been distributed across these particles? Same number of particles, but a lot more energy that has been distributed. And there's a lot of disorder. Yes? Okay, give me a moment, please. I need to extend the class. Okay, there we go. So there's a lot more disorder, and therefore one can confidently state that there is a lot more, sorry, give me one moment please. Here we go. That this, the gaseous state, is a much higher entropy situation as compared to the solid or the liquid state. Is that fair to say? Rest of you, is that a fair statement or no? Again, I will repeat, what was entropy dependent upon? Entropy was dependent on the total amount of energy that was distributed and how it was distributed. Both these. The greater the distribution, the more the entropy, the more the disorder. Okay, remember, entropy is energy disorder. How disordered is energy? Okay? Alright, now here's what I'm going to do. I'm going to change this, I'm going to go back to, or I'll leave it as a gas. And I'm now going to change the substance to water. And now take a look at what happens. Now, in addition to the translational motion, can you see that the water molecules are also rotating about their own axes? Can you see that? I'll wait for all of you to confirm that you can see this. Harish, Sanjana, Rohan. So now, would it be fair to say that that's funny. Yeah, that's true. That is true. Okay, but would it be fair to say that in addition to vibrational motion or translational motion, which means motion in a straight line, they also have rotational motion now, which means that they have kinetic energy as we know it, translational kinetic energy, but they also have rotational kinetic energy, which means that the total amount of energy that has now been distributed is even more than earlier. Is it fair to say that? There's also rotational energy in addition to the translational energy that existed earlier, right? Which means that the entropy of this system is, wow, it's like really much more than any of the others, okay, that we just saw with neon. Clear? Getting a sense for what entropy is? That was the idea of this experiment. You should get a sense for what entropy is. It's how disordered is energy, okay? So how much energy, how much, so if you have a certain amount of energy, how much is it distributed? How many particles is it distributed over? How many ways is it distributed? So here it's distributed as rotational and translational kinetic energy, whereas in the previous case it was only translational kinetic energy. All these things matter. There are many things that matter. I can hardly go through all of them. I can just give you a sense for what entropy is. It is energy disorder. If you have got that much, then you have taken away a lot. You have taken away what this experiment could offer you. Alright? Alright, I'm going to pause the screen. Can we go back to class now, please? How does this apply to chemical systems? Again, let's come back to this. That's the beauty of its Kirti. It's so that joules, the idea of joules, yeah, or the ways in which it can be distributed depends on the temperature, and this is something you learn in thermodynamics in the 11th. All right, so it is all very neatly captured by the idea of temperature. Can you see temperature is the denominator of that unit? So the ways, the many ways in which it can be distributed is actually very neatly captured by what temperature itself is. Do you know that, just let me give you a hint. You must have studied in gaseous state kinetic theory that temperature is a measure of average translational kinetic energy. Yes? So it turns out, it's a very good question, the temperature term actually captures the distribution extremely well. Alright? This is the first point. The numerator J, okay, or I'm sorry, numerator, which is energy in joules, also has to be a specific form of measurement of energy. It can't be any energy, okay? It's a way that you measure it so that it accounts for all possible energies. So it's a little complex to explain here, but you will, I promise you, you will understand this idea in the 11th standard when you do thermodynamics in detail. For now, my goal is simply to give you a sense for what entropy is, because when students come to the 11th standard, they have no idea of what entropy is and they get completely lost when we teach thermodynamics. If you walk away from this class saying, okay, I have some sense of what entropy is, the greater the energy, the greater the entropy. The more the particles is distributed over, the greater the entropy. The more the modes of translational as well as rotational motion. That's how the energies are distributed. The more the entropy. If you have that much of an idea, that's enough for now. Okay? But that's a good question. That is a good question. All right, so let's figure out how do we apply this to chemical reactions. Okay? Did Ashish teach you the second law of thermodynamics? Or some form of it? Spontaneity, yeah? Spontaneity and entropy. That spontaneous reactions are those in which entropy increases. He taught you this, yes? Amol did, okay, sure. So now let's look at these equations, keeping that in mind and our understanding of entropy as we just figure it out from this lab. Look at these two equations in front of us here. Okay, the first is sodium reacting with HCl to produce sodium chloride and hydrogen. The second one is sodium hydroxide reacting with HCl to produce sodium chloride and water. Can you see that in the first reaction, on the right hand side, there is no gas on the left, but there is a gas on the right? Can you see that? So is it fair for me to say that the entropy change in this reaction as we go from reactants to products is huge? Because you've got a gas on the right hand side, and gas are very high entropy creatures, right? Is it fair for me to say that entropy should increase massively in this first reaction because a gas is being created? All right, very good. How about the second? Can you see there's no gas on the left and no gas on the right? Yes, rest of you, can you see this? No gas on the left, no gas on the right. Is it fair for me to say that the entropy change is small in this reaction? Am I justified in saying that? People, can you hear me? Not hear me? Hello? Let me repeat the question. Am I justified in saying that in this second reaction, the change in entropy is much smaller than in the first reaction? Okay. Therefore, can I say now, knowing my understanding of entropy and spontaneity, can I say that the first reaction will be much more spontaneous because it involves a greater change in entropy? Can I make that judgment call? It turns out that's exactly what happens in real life. This first reaction is explosive. Okay? And I have a couple of videos, I'll put them out here. There's some links, and you can judge the spontaneity for yourselves. Alright? Over here. One of them is taking some sodium, dropping it into HCl. The second is taking some sodium chloride and reacting with HCl. And you see that one is very controlled, the second reaction is extremely controlled. This first reaction is explosive because it wants to happen so fast because of this entropy change. Is this clear how entropy applies to chemical systems? Okay, let me see if there's anything else. Give me one moment. I think that brings me to the end of this class. If you have any questions, please fire away. If you don't have any questions, here is the feedback link and you're free to leave. So, Asmita's question. So, a reaction where a gas is formed is always fast. Not necessarily. Not necessarily, Asmita. Why would that be? Let me give you an example. Okay? Here's an example of a reaction. Let me balance this. I would require, I put 3 here and I would put 2 here. Can you see that a gas is still formed here? But can you see that I have more molecules of gas on the right and less on the left? I'm sorry, more on the left and on the reactant side and less on the product side. Would you expect this to be spontaneous from your understanding now? Not really, exactly. All right. So it depends on what's happening from reactants to products. Okay, not just the fact that there's a gas on the right hand side. All right. Is that clear? Okay, very good. Any more questions? How do magnets exert force? Right, we'll probably come to that in one of your next lectures, so we'll come to that. How do they get their energy? It's there's an idea called a field, a magnetic field, okay? And that's what, it's how certain particles behave in that magnetic field. Again, when we do chemistry, we'll get, in the 11th standard, you'll understand the idea of why some species such as iron are actually magnetic and the others are not. Why some ions are attracted to magnets, others are not. We'll explore. You don't know enough for me to explain in that much detail yet. Okay, Sanjana has a question. Why did we conclude that the reaction had greater change in entropy simply because there was a gas evolved without other things? Because the other things were extremely small. The fact that the biggest influence on entropy is the fact that you had no gas here and you have a lot of gas here. You have 1 mole of gas on the right hand side. This is one of the biggest influencers of entropy. Now, I'm comparing these two, okay? I'm not looking at the reaction in isolation. I'm comparing these two. I have the same product being formed on the right hand side, but the other product being formed in one case is a gas, in the second case it isn't. So I'm comparing these two. Alright, so I'm not just concluding on the basis of looking at one reaction. I'm simply comparing these two, and I'm saying that because of this effect, this one is going to be much more spontaneous as compared to this one. That's all I'm saying. Alright, Sanjana, I'm not saying that this one is going to be, just by looking at this, I can't say that this is going to be massively spontaneous. Is that clear? I'm just comparing these two and saying between them, the first one will be much more spontaneous as compared to the second. That is all I can say. I cannot just look at a reaction and say, is it going to be spontaneous or not? Does that answer your question? Okay, very good. Any more questions? All right, well, look, I'll put up these videos.